Okay, Bose-Einstein condensates explained in easy words.
State of matter is formed when atoms are cooled to temperatures near absolute zero, which is equivalent to 0 Kelvin or negative 273.15 degrees Celsius. During that super chilled phase, the atoms possess minimal energy and exhibit minimal movement. Consequently, they aggregate and become indistinguishable from a physical standpoint, behaving as a single atom. Satyendra Nath Bose, an Indian physicist specializing in theoretical physics, laid the groundwork for this revolutionary theory. He is also credited with discovering the boson, a subatomic particle that now bears his name.
Yeah, so multiple atoms act like one atom. Here's the first problem. We were taught that atoms are not bosons, that they're fermions, meaning they cannot hold the same location in space and time at the same time. Okay, so fermions, that's the same reason my hand doesn't go through the microphone. It's being rejected. It's being repelled. But the idea of a Bose-Einstein condensate is you can get your atoms to begin to act like bosons. And boson is like light, where you can focus down your light into a laser to a single point. And what does that do? That increases the energy. That increases the density, the energy density of that particular focused point. So if we can do that with matter, then we can create a matter wave beam, coherent matter wave beam, perhaps. One of the things that I found out was that coherent matter wave beams, the thing that we saw Charles Chase discuss, are produced by Bose-Einstein condensates. Bose-Einstein condensates can produce coherent matter wave beams. So that was not something that I was expecting to find out. There's obviously this connection between Bose-Einstein condensates and matter wave beams.
Albert Einstein, a German scientist famed for the special theory of relativity. Einstein then submitted these ideas to Zeitschrift für Physik, a German language physics journal of the time. To generate the Bose-Einstein condensate, the first step is to obtain a cloud of gas. A typical example is the gas of rubidium atoms. The next step is to use lasers to remove the atom's energy and cool them down. An evaporative cooling method is utilized for further cooling until the atoms are close to absolute zero. At this stage, the atoms assume the same quantum states and operate as a single entity. If you were to measure their location at this point, you would observe a blurred ball rather than individual atoms.
If you were trying to observe this quantum state, this Bose-Einstein condensate, you see a blurred ball instead of individual atoms. So the idea of the Bose-Einstein condensate, to me, conceptually is connected to this idea of rebuilding the wave function. Because now your matter, your atom, your rubidium atom, is no longer at one particular point. Now it's in this like blob, basically, right? That's what that's saying right there.
Bose-Einstein condensate was initially predicted in 1924 and 1925, but wasn't created until 1995 by American physicist Eric Cornell and Carl Wieman.
America winning again, chat. America wins again.
Using rubidium atoms. Wolfgang Ketterle, a German physicist, produced the condensate the same year using sodium atoms. In 2001, these physicists won the Nobel Prize in Physics for achieving Bose-Einstein condensation.
Look at the time frame on all these things. All this science that we've been discovering is usually between the mid to late 90s and the early 2000s. Everything is converging on that 2005 dense plasma focus paper by Frank Mead, George Miley, and David Froning.
Studying particles at near absolute zero temperatures and creating Bose-Einstein condensates has important implications in areas like quantum computing, superconductivity, and scientific research. One example of how researchers use BECs is to gain a better understanding of quantum entanglement. This phenomenon in quantum mechanics explains how particles that are entangled can affect each other's state, regardless of their physical distance. quantum entanglement is crucial for many technologies, including the fast-emerging field of quantum computing.
So there we go. What's the point of the BECs, these Bose-Einstein condensates? Well, one thing is they're connected to quantum computing through entanglement. And guys, if you didn't watch last Wednesday's live stream 1 week ago today, what was it called? Solving Schrodinger's equation. Solving Schrodinger's equation, the whole idea was how can we solve entanglement through the ether regardless of distance? We can solve Schrodinger's equation and figure out the vortex motion through the ether that we don't see, that's in an extra dimension.
We have created a separate video about quantum entanglement. You can find the link in the description of this video. Bose-Einstein condensates, BECs, have various practical uses in precision measurement and sensing technologies, which have led to advancements in detecting gravitational waves, creating navigation systems, and improving magnetic resonance imaging, MRI.
Okay. So he's saying all the right things, right? He's saying quantum sensing, MRIs. What else was he saying here? Navigation systems, gravitational waves. So Bose-Einstein condensates are connected to everything. In fact, the more I looked into Bose-Einstein condensates, the more I'm convinced we are looking at Bose-Einstein condensates in the MH370 videos. The orbs, I think, are a Bose-Einstein condensate.
Navigation systems and improving magnetism has already aided research in quantum atomic matters, which hold great MRI. In addition, BECs have been used to develop atom lasers, which hold great potential for the precise manipulation of atomic matter.
That's a matter wave right there. An atom laser is a matter wave beam.
This advancement has already aided research in quantum optics and lithography.
Hello. So this was actually the reason why I got excited about this. Take a look at this. Quantum optics. Quantum optics, was that same as the optic vortices that we were looking into last week? And then
lithography.
Lithography, chat. Lithography. Lithography is microchips. So Bose-Einstein condensates have improved lithography in microchips.
In 2018, a groundbreaking experiment was conducted on the International Space Station. Rubidium atoms were cooled to nearly 1/1,000,000th of a degree, setting a new record for the coldest experiment ever conducted in space.
So this one will explain a little bit more about the Bose-Einstein condensates from a scientific perspective. Oh, does this one have no sound? All right, maybe I'll just go. Can I just mute it? How about I just mute it? I'll just mute it and tell you what it says. Okay. When the gases cool down, the atoms slow down and their energy level decreases. So what you're going to see here is when they decrease, the atoms start to begin as waves as the temperature decreases. So you can see their size increases. So take a look at how their size is increasing. This could be imagined as their wave function. So their wave function is rebuilding, right? The wave function rebuilds and they kind of just blob together. And then when they finally reach the lowest state, this is when they're at the lowest energy state right here. You can see the energy level on the left on the chart is at the lowest state. And now they've coalesced into this wave function. It's turning particles into waves. Exactly. So why is Bose-Einstein so huge? Bose-Einstein condensate's big because we're turning particles into waves. Turning particles into waves. So, I mean, my first thought is, well, if they're turning the plane into a wave function, that could be a way they could do it. Another thought is that this might be a way to produce a coherent ball of plasma. Those are some thoughts that I have right off the bat. Let's let this finish out. So they form a single collective quantum wave called a Bose-Einstein condensate. So that's what a Bose-Einstein condensate is. Room temperature Bose-Einstein condensates. So first question, right? First question we have, those atoms supposedly had to be at absolute zero. Is there a way to make a Bose-Einstein condensate that's not at absolute zero? Of course there is. Of course there is. And this guy figured it out back in 2013. This predates the MH370 videos. Scientific milestone, a room temperature Bose-Einstein condensate. A BEC is an unusual state of matter in which a group of boson particles can exist in a single quantum state, allowing scientists to observe novel quantum phenomenon. Okay, so how did he do this? Our experiment was done with a very thin wire, a nano wire made of aluminum, gallium, and nitrogen. So how do they, like, what does it mean, though? What did they turn into a Bose-Einstein condensate? He says, specifically, he states that because the polariton BEC is a coherent state of matter, it is possible that the light emitted can one day be controlled and used for sensitive instrumentation measurements. You know what this reminds me of? I still don't really even understand what he did here. Yeah, it reminds me of the room temperature superconductor, but it also reminds me of that. Wasn't there something about light, people like liquid or solid light or something like that? Let me Google that real quick. I wonder if solid light is a Bose-Einstein condensate. Somebody was like, they were like playing with light. Yeah, scientists turn super solid light into a super solid. Oh, and then what I was trying to figure out is if they can make a continuous Bose-Einstein condensate. So there actually is another Nature paper called Continuous Bose-Einstein Condensation. BECs are macroscopic coherent matter waves that have revolutionized quantum science and atomic physics. This is 2022. A long-standing constraint for quantum gas devices has been the need to execute cooling stages time sequentially, restricting these devices to pulsed operation. Here we demonstrate continuous Bose-Einstein condensation by creating a continuous wave condensate of strontium atoms that lasts indefinitely. The coherent matter wave is sustained by amplification through Bose-stimulated gain of atoms through a thermal bath. By steadily replenishing this bath while achieving 1,000 times higher phase space densities than previous works, we maintain the conditions for condensation. So this is saying we can produce maybe a matter wave beam, but definitely consistent, persistent, coherent Bose-Einstein condensate. So we can create a quantum wave function that will last. It's going to stay there. And you can see why this would be relevant for quantum computers. Coherent matter waves, published in Journal Physics B. So studies of coherent matter waves and Bose-Einstein condensation are now an important and growing part of atomic, molecular, and optical physics around the world. These investigations are giving us new insights into the nature of coherent assemblies of ultra-cold atoms. These mesoscopic systems, newly available in the laboratory, are accessible to first principles theory, making them a superb testing ground for many-body physics. Many-body physics. Huh. That's a pretty interesting terminology they're using right there. We can control and manipulate matter waves using resonant frequencies. This was just something that people were digging up stuff when I was posting about coherent matter waves. And one of the people said it would be essentially possible to make matter programmable, giving us the ability to assemble, disassemble, move, and repurpose atoms and molecules with laser-like precision. That's what coherent matter wave beam could allow for us to do. Plasma, coherent matter wave beams, Bose-Einstein condensates, fusion. How does this all come together? How do we do these room temperature Bose-Einstein condensates? How do we make these plasma balls? This is a clip from Gary Stevenson from a couple months ago. Gary Stevenson, by the way, is rising up the ranks of people that I'm definitely in my crosshairs in terms of people that know about this technology. I've chatted with Garrett Modell. I don't think he knows. I had a communication with Larry Forsley. I get the feeling like he doesn't know either. Charles Chase, Hal Puthoff, Eric Davis, those guys definitely know. And I get the feeling like Gary Stevenson probably knows as well. So here's Gary Stevenson, especially after watching this. Here's Gary Stevenson talking about producing gravitational waves with plasma in a quadrupole oscillator. What? When did Gary Stevenson start talking about plasma? This guy, I have a feeling, knows way more than I've previously assumed. I just thought he was like a gravitational wave guy, but here you go. Let's just listen to what he says.
Another one that I've been working on, as well as Andy Beckwith has been doing some work on, is it possible to create plasma oscillations in a tokamak that could create gravitational waves? For gravitational wave, you need a third derivative of the quadrupole moment. So how do you get that? Well, if you have this sloshing back and forth of plasma at a specific frequency, that sloshing back and forth has a third derivative. And if it's sloshing back and forth in a quadrupole manner, then you got a third derivative of a quadrupole moment. And that would create then a gravitational wave orthonormal to the movement of the plasma. So I first worked out this in 2003. I revisited it for a high-frequency gravitational wave summit in Chengdu in China in 2017. We looked then at a burning plasma because we weren't getting really enough delta mass to be able to measure anything with.
So, okay, let me help explain it for you guys. He's saying you're going to have movement orthogonal to the motion of the plasma. Orthogonal is like perpendicular, okay? But imagine in 3 dimensions, right? So that's why we use our right-hand rule in electrical engineering. So you have this one going left, this one going forward, this one going up. 3 dimensions. Pretty simple. So he's saying that if we have our plasma oscillating, you can produce a gravitational wave. And he's saying you're having it slosh back and forth. So imagine you're in the bathtub. You're in the bathtub filled with water, and you start rocking back and forth. The water is going to start to make waves, right? What Gary Stevenson's saying is that if you change the force with which you're rocking, let's say you rock forward at 2 units of force, but you only rock backwards with 1 unit of force. So 2 units forward, 1 unit back. 2 units forward, 1 unit back. You create an asymmetry. And he's saying this asymmetry can be exploited.
Just ordinary plasma. It has to be undergoing fusion. So we have to be oscillating between fusion nodes, where fusion node burning, and continue. Now that still doesn't.
It has to be fusion nodes, he says. He's just casually dropping the F-bomb right here. Fusion. Doesn't mean, you would thought the F-bomb meant something else. No, it means fusion. Just like how the N-word means nuclear. You guys just heard him say fusion, right? I wasn't just imagining that.
To be undergoing fusion. So we have to be oscillating delta mass to be able to measure anything with just ordinary plasma. It has to be undergoing fusion. So we have to be oscillating between fusion nodes, where fusion node burning, and continue. Now that still doesn't get us to propulsion. What we need to do then from these gravitational waves is do rectification of the waves. And so I had written that up during the Gertzenstein paper that I gave, I believe in the 2007 timeframe. It was one of the STAVE conferences. And that's kind of in the lower right. It's a little bit of an eye test. I'll walk you through the steps, but this is going to be available for download. Tim, you've got this now that I've uploaded it, so feel free to make this public.
The way he's like, feel free to make this public. Like, was this some shit that he presented to Boeing? Do you guys realize, like, Gary Stevenson's worked for NASA, Boeing, ITT? Dude's got Black Project Engineer written all over him. And if you look up his career, he's, like, pretty esteemed as well. So he's just out here explaining, like, hey, if we have these plasmas creating fusion nodes, and we're, like, pulsing it, we can cause our plasma to oscillate, and that plasma oscillation can produce thrust.
And if you slash in one direction very quickly, and you slash in the other direction very slowly, then you get an asymmetry that comes out of that third derivative. Faster, higher frequencies, the third derivative of those is much stronger than a very slow mass movement in the relaxation direction. And so that if you have 2 of those, then 2 of these toroids situated in such a way that the gravitational waves add at the front of the craft, and they also add in the opposite direction in the back of the craft, you can get forward motion. And so that's what's depicted there in fast impulse, slow relaxation, and that's doing your quadrupole rectification just geometrically, where you're getting constructive interference on one edge, and then you're just throwing overboard the gravitational waves on the other edge. So this could never be more than 50% efficient. In fact, very, very probably very much less so. But it is one potential route to go for rectifying quadrupole gravitational waves.
Rectifying quadrupole gravitational waves, chat. Rectifying quadrupole gravitational waves. Try to say that 5 times quick. Good luck. Best of luck to you.